So today and tomorrow, I'd like to give an introduction to tropical geometry. And if you wonder where the adjective comes from, we better leave that for the coffee break. Today, I'd like to talk about tropical convexity, convex polytopes in tropical geometry in particular. And there's a joint paper with Mike Devlin, who's a postdoc here, and the paper is somewhere here, and it's intended for the proceedings of this very nice workshop. And tomorrow I'll talk about tropical algebraic geometry, and there are two papers on the archive, one with David Speyer, who's in the audience, another one with Richter Gebert and Theobald, both not entirely unfamiliar names in this community. So here are some examples of tropical polytopes, specifically tropical triangles. So in the tropical forest, there's a lot more diversity. So these are all examples of convex hulls in the sense to be defined of 3 points A, B, and C. Where can we turn the light off? No? Can you turn the light off a little bit? Okay, great. So the algebraic structure we begin with is the so-called tropical semiring, and that's also known as the MIN plus algebra or Fahrplan algebra in German. And so this is the set of real numbers with two operations, tropical addition and tropical multiplication, and the sum of two numbers is defined to be the minimum of the two numbers. So A plus B is defined to be the minimum of A and B. And the product, the tropical product of two numbers is A plus B. So here are two examples. 3 plus 5 is 3, and 3 times 5 is 8. Takes a little bit time to get used to. 0 is the multiplicatively neutral element in this algebra, and infinity is the additively neutral element in this algebra. So sometimes we extend the real numbers by plus infinity, but that's not very important. So we can either take the reals or the reals together with plus infinity. And it satisfies many of the familiar rules, axioms that you know for arithmetic, distributivity, and so on. So I said already, infinity is the additive neutral, 0 is the multiplicative neutral. And this is a special case of what's sometimes called idempotent semirings. So it's idempotent in the sense that for any number A, you have A plus A plus A plus A is equal to A. Well, what is a semiring? So I guess there is no additive inverse. So semi in the sense that you don't have all the inverses that you like to have. So it's the set with these operations. So we'd like to do geometry in this set. So let's look at R to the n, which is n tuples of real numbers. So if we could agree on what a semiring is, then we would probably also agree what a semimodule is. Well, a semimodule for a semiring is the same thing as a module for a ring or a vector space for a field. So R to the n you can act on. Namely, you can add two real vectors just coordinate-wise. So this is simply the vector where coordinate-wise you take the minimum of AI and BI. And then there's also scalar multiplication, where you have a scalar, a real number lambda. Lambda times a vector A1 up to AN is simply coordinate-wise lambda times A1 plus lambda times AN. And in ordinary arithmetic, this would be scalar addition, right? So you have a vector, and you add the scalar lambda to each and every coordinate. Okay, so we have addition of vectors, we have scalar multiplication, so we can talk about linear combinations, tropical linear combinations. So here's a little example. So 7, so this is in 3 space, so we have a linear combination of two blue vectors in 3 space. 7 times the vector 1, 2, 3 plus 5 times the vector 4, 2, 0 is the vector 8, 7, 5. Okay, so as I said, it's not hard, it just takes a little practice. So the left summand, 7 times 1, 2, 3, that's the vector 8, 9, 10. The vector on the right is the vector 9, 7, 5. And then we take the minimum in each of the 3 coordinates, and unless I made a mistake, that turns out to be 8, 7, 5. Okay, so this is how we form linear combinations in the tropical semiring. Okay, so here's the key definition. A subset S of R to the n is said to be convex, tropically convex, if it's closed under taking linear combinations. Okay, so here convexity, we allow arbitrary coefficients, lambda and nu, and this might require some discussion. You might be thinking about the 0 and 1, the old-fashioned additive and multiplicatively neutral element. But if you do it the right way with the corresponding neutral and multiplicative and additive neutral elements in the tropical semiring, then you realize very soon that you should actually allow all multipliers to get the notion of convexity. So subset of R to the n is convex if whenever 2 points, A and B, are in the subset S, then, and you form any tropical linear combination of the 2, then that combination should also be in. So for instance, the point 8, 7, 5 is in the convex hull of 1, 2, 3, and 4, 2, 0. So then the convex hull of a subset S in R to the n, which I'll denote T-conv, the tropical convex hull, is the smallest convex subset of R to the n which contains S, just like in the usual way. Now, this is some kind of notion of convexity. Of course, there are many, many notions in this community. People know many notions of discrete convexity. One that's really very interesting is the directional convexity that was studied by Matuszek and others. That's much, much harder. What I'm talking about is much, much easier than, say, directional convexity in the sense of Matuszek. You have a lemma that says the convex hull, which we're familiar, people who look at any kind of algebraic structures will recognize this. The convex hull is actually the set of all finite convex combinations. So you can characterize the convex hull of S as the set of all finite linear combinations V1 of vectors V1 up to VR, each coming from S with arbitrary multipliers lambda. So you have both the extensive and sort of the intensive definition. Okay, so we've reached the third transparency, and that's the third projector, so maybe this is a good time for a little quiz. So there are lots of people who know about basic algorithms in computer science and discrete math. So the question for the audience is, what's Dijkstra's algorithm? Well, I already gave away the answer. So Dijkstra's algorithm, the way we teach it to our undergraduate students, you take a graph or let's say an undirected graph for simplicity with n nodes, and on the edges you have some lengths. So let's say the flight routes of United Airlines, and then you're interested for any 2 points you like to calculate the minimum distance from, say, San Francisco to Milwaukee, and then so this you also want to organize in an n by n matrix, and there's a very familiar algorithm called Dijkstra's algorithm, and it amounts to successively multiplying a matrix with itself in the tropical semiring. Yeah? So you start with the n by n matrix, where in position row I, column j, you have the direct distance between 2 nodes that have a direct link. So San Francisco, Salt Lake City, you write the distance, and then if there's no direct link, you put plus infinity. That's an n by n symmetric matrix, and you simply calculate the nth power tropically of this matrix, and that is called Dijkstra's algorithm. So once you think about it a little bit many of us, all of us, in fact, have seen tropical calculations in one way or another. Okay, so to explain these pictures and to go a little further, let's talk about projective space. So here, as I said, things are very, very easy. So we're going to identify Euclidean space and projective space. So it turns out if you have a convex subset S of R to the n, then whenever there's a point in there, well, then if you scalar add or scalar multiply any lambda, that will also be in there. So if V is in the convex set, then by definition, lambda, tropically times V, will be in that set for any lambda. So back in ordinary arithmetic, this says that S plus the line spanned by the vector 1, 1, 1, 1, 1 through the origin will also be in S. So any tropically convex set, by definition, will be invariant under shifting by the vector with all ones. Okay? That's an easy observation. So in order to draw pictures a little simpler, we mod out this linear space. Pardon me? I couldn't. Yes. Everything, unless otherwise stated, everything is tropical in this talk. Well, we'll come to. So when I refer to ordinary polytopes, I will call them ordinary polytopes. Okay. If I say just convex hull or convexity, so this is for tropically convex sets. So tropically convex set. So to make things a little simpler, I will therefore identify S with its image in the R to the n modulo the line, the linear space spanned by the all 1 vector. So that's an n minus 1 dimensional space, and I'm going to call that tropical projective space. So this is tropical projective n minus 1 space. So tropicalization is an operation that takes multiplication and turns it into addition. So if you think about the ordinary definition of projective space, ordinary projective space you get from n-dimensional space by identifying two vectors if one is the scalar multiple of another one, and we're actually doing the same thing here. So this is the notion of tropical projective space. And the toughest thing about this space, it doesn't actually come with the canonical basis as much as I would like it to. Okay, so let's draw points in the plane. So the pictures I'm going to draw in the plane. By convention, I will normalize points so that the first coordinate is always 0. Right? So in ordinary projective space, almost all points can be normalized to have first coordinate 1. That's the multiplicatively neutral element. We do the same thing here, but except it's again simpler. Every point can be normalized to have first coordinate 0. So if you give me a point A1, A2, A3 in the tropical projective plane, so I rewrite it as 0, A2 minus A1, A3 minus A1, and then I simply take the last two coordinates and draw it in the usual plane. So for instance, let's do an example. So let's say this black point here is the origin. And really, if I wanted to have a symmetric version of this, then these three blue directions are the three unit directions. Very familiar to people who look at representation theory. So for instance, then the point 1, 2, 3 would be drawn here, right? Because 1, 2, 3 is the same thing as 0, 1, 2. So I draw that in location 1, 2. And then down here, 4, 2, 0. That's the same thing as 0, negative 2, negative 4. And then, then I do this calculation over there. I form, for instance, this point convex combination. And I get this point 875, which lies on this green tropical segment. So it turns out the green tropical segment here is the union of two ordinary segments. And this is these green points, that's the set of all points that you get by forming arbitrary tropical linear combinations. So if I replace the multipliers 7 and 5 over here by arbitrary real numbers, and then I drew it in the plane, then I would get exactly the points along the green connection between 4, 2, 0 and 1, 2, 3, and then here a couple other black points in the tropical projective plane. So maybe this would be a good moment to pause for a question.
So what is the point where those two rays meet?
What is the point? Yes, so that's a special point. Actually, the next transparency will talk about it, but it's actually the point 0, 1, 0. Okay, so I'll. So this will be answered by.
Actually, that's drawn wrong. You need to shift the diagonal line down by 1.
It's wrongly drawn.
Yes. The diagonal line needs to be shifted down by exactly 1 unit.
Oh, really? I see. Did I make a mistake? Okay, I see. So this should be 0. Oh, I see. I see. So take this green thing and move it all down the one. Thanks for paying attention. So it's a typo in the transparency, but I think the idea is clear. Okay. Okay, so line segments. So what are line segments? So turns out that the line segment between 2 points, if you take 2 points, x and y, in projective n-1 dimensional space, then, well, what's the line segment? That's the convex hull of those 2 points. That turns out to be the concatenation of at most n-1 ordinary line segments. So the picture on the left-hand side is n equals 3. And if x and y are fairly general, then it will be exactly n-1 line segments. And here's a little example that maybe will clarify and answer Eli's question. So let's say we are in projective 3 space, so n is 4, and then we can sort of shift coordinates so that x is the point 0, 0, 0, 0, and y is some other point with coordinates y1, y2, y3, y4. And let me assume, for simplicity, that the coordinates are strictly increasing. Then the convex hull of x and y is the union of 3 ordinary line segments and can be described as follows. So we start at the point x. Now the point x is really the same as the point y1, 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 y1. And then what we do is we simply increase sort of tail strings of coordinates. So for instance, we go from here to here and we simultaneously increase the last 3 coordinates until they hit y2. So then this first breakpoint is y1, y2, y2, y2. Then we go on. We increase the last 2 coordinates until they hit y3. And then finally, the last stretch all the way goes to y. So it turns out that this is the convex hull of x and y in this example. And it's not hard to generalize that and write down a more invariant formula.
What singles out that particular ordering?
This one, none. I mean, none. I just without losses. So if you switch the coordinates, then it's corresponding. And you can also see if one of these strict inequalities, say this one, became a weak inequality, then there would be no bend. I mean, the picture would look like this, but it would continue straight across one of these blue points. Okay, so let's summarize a few basic facts about tropical convex sets. So I'm going to give about 5 or 6 of these, and some are very easy. So this one is very easy, right? Follows straight from the definition. The intersection of 2 convex sets is convex. Coordinate projections preserve convexity. So if you are in n space or in tropical n-1 space, and you look at the operation of erasing some of the coordinates, then the image of a convex set will be a convex set. And that's because erasing coordinates is an example of a tropically linear map. So ordinary linear maps will not preserve tropical convexity, but of course tropical linear maps will preserve tropical convexity.
I mean, those are maps that are linear with respect to the center.
That's right. So there's a tropical linear algebra, and we've seen that in Dijkstra's algorithm. So you can do matrix vector operations in the familiar way. And so tropically linear maps will preserve convexity. But ordinary linear maps generally will not. So then you can sort of ask about the relation between sort of ordinary convexity and tropical convexity. So it turns out that certain ordinary half spaces are actually tropically convex. So if you take half space defined by an inequality of the form xi minus xj is less or equal to something. So it turns out that that's actually tropically convex. So that's an example. So these are tropically convex sets. And then by property 1, well, if you intersect any of these, then you get polyhedra and polytopes defined by inequalities of this particular form. And those turn out to be tropically convex. And these are, in fact, all polytopes that are both ordinary polytopes and tropical polytopes. So to be both an ordinary polytope and a tropical polytope at the same time, the linear forms that define that polytope have to be of the form xi minus xj less or equal to c. And I see some people in the audience itching. What about other root systems? Okay, so the Cartesian product of convex sets is convex. That's easy. There's a statement that's a bit harder, but the proof we have in the notes is not so difficult, but it took me a little while to figure this out, and later we'll see a conceptual reason. So tropical subsets are always contractible. So this should be tropical convex subsets. Sorry, there's a word convex. So convex subsets are always contractible, so that's clearly true, for line segments. And we'll see more pictures, so they're always contractible polyhedral complexes. Caradeo-Torres theorem holds. So if you have a subset S of projective n-1 space, and you have a point in its tropical convex hull, X, then X is already in the tropical convex hull of at most n points, V1 up to Vn. So this is exactly the statement of Caradeo-Torres theorem. And that's one of the indications in which sense this is much easier than, say, directional convexity. So if you've read Matuszek's papers on directional convexity, Caradeo-Torres fails. And for other notions of convexity, it fails as well. So these basic theorems hold. So you can maybe test your understanding by trying these slightly harder questions. So what about tropical tetrahedra in 3 space? So we've seen some pictures at the very beginning of tropical triangles in the plane. So Caradeo-Torres theorem says if you have many, many, many blue points in the plane, and you have some other point, X, that's in the convex hull of lots and lots of blue points, then it's already in the convex hull of only 3 blue points. So if you're good at visualizing these things, try to visualize convex hulls of 4 points in 3 space. Another question is, what about these polytopes that are both ordinary polytopes and tropical polytopes? They're quite interesting. And so maybe a question you could think about is, how many vertices can such a polytope have? And I think some is known, but not a lot is known. I think there's still a very good open question, for instance, to characterize the F-vectors of both ordinary and tropical polytopes. Paco?
Shouldn't the A in the second picture there be on the left?
Oh, yes. Good, thank you. So this A... Is that what I want? Okay, so this picture is incorrect. I hope the other 3 are correct. In the notes, everything will be perfect. Okay. Ordinary vertices, say. Okay. Okay, so these are some questions. Let's talk about hyperplanes. So actually tomorrow, the topic will be tropical algebraic geometry. And sort of the starting point of algebraic geometry is linear spaces. And so I'm not going to say very much about that, just sort of a preview. And of course, in ordinary geometry, hyperplanes are convex sets. In fact, linear spaces could be defined as sort of maximally convex sets relative to a fixed dimension, right? So if you're interested in convex subsets of R to the n of a fixed dimension k, and you want to make them as big as possible, then you get to the definition of linear space. So you could actually define linear space this way. But here's the definition of hyperplane that we'll use. So we're given a tropical linear form, a1 x1 plus 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 an xn. So then the hyperplane H that's defined by this linear form in n-1 projective space is the set of all points with the property that the minimum, so evaluating a linear form means calculating a minimum of n things. And you're interested in those points where the minimum is attained at least twice. Okay? So calculating this linear form means calculating in ordinary arithmetic this minimum of a1 plus x1 up to an plus xn. And then if you look at the set of all points where that minimum is attained 2 or more times, that we call the hyperplane. And then hyperplanes are convex. Now, if hyperplanes are convex, then by property 1, any intersection of hyperplanes is also convex. And it turns out that tropical linear spaces are always intersections of tropical hyperplanes, but the converse is not true, and we'll see tomorrow why. So every tropical linear space is an intersection of tropical hyperplanes, but not conversely. So you can form intersections of tropical hyperplanes that don't deserve the term tropical linear space. I just put this up to sort of state a version of a separation theorem. So this is Farkas lemma, and here's a way to state tropical Farkas lemma. So if you have a tropical polytope P, and you have a point x in n-1 space, either x is in the polytope P, or there exists a hyperplane H which separates the point x from the polytope P. And one way to say the separation is the following. So here's our polytope P, and the hyperplane will be this blue picture consisting of 3 half-rays. And this sort of tripod of half-rays separates the point x from the polytope P, and algebraically let k be an index of which this upper minimum is attained, then you have a violation for every point in the polytope. Okay? That's the correct way of saying separation.
So it could be, well, in fact, it is the case that sometimes the hyperplane will necessarily have to intersect the polytope, but it may still separate it.
That's correct. One of those triple things will separate. Now, there's separation. There's a nearest point map. There's a metric on tropical projective space that's induced from the L infinity metric on R to the n. So if you take ordinary n space, you have all these norms, right? The L2 norm, the L3 norm, the LP norm. They're all tropicalized to the same norm, namely the L infinity norm. So L infinity on R to the n is the common tropicalization of all the LP norms for finite p. And that descends to a norm, a distance on tropical projective space. People who know about these things is sort of the tropical Fubini-Studi metric. And this is actually, this separation theorem actually gives rise to a nearest point map. So if you have a tropical polytope and a point outside, then there's a unique map, or a convex set in general, that you can project on. Okay, let me state a theorem. So maybe this is the main theorem of our manuscript. So it says the following. The combinatorial types of tropical polytopes. I haven't actually defined this yet. So there is a notion of combinatorial type of tropical polytope. And it turns out that the combinatorial types of tropical polytopes that are the convex hull of R points in n-1 dimensional space are in bijection with something that's well studied and well loved among the polytope community, namely the regular polyhedral subdivisions of the product of two simplices. So the n-1 dimensional standard simplex times the r-1 dimensional standard simplex. Okay, so there's a correspondence between regular subdivisions of products of two simplices and tropical polytopes. Let's do an example. Simplest instance of this correspondence. So let's look at n equals 2, r equals 3. Now, it's sort of amazing, right? The second formulation is symmetric in R and N, right? If you triangulate if a product of two simplices, there's a symmetry in R and N. While, I mean, taking the convex hull of R points in n-1 space, on the face of it, is something very different from taking the convex hull of R points in n-1 space. So this is sort of interesting already. N points in R-1 space, exactly. So anyway, so let's look at this symmetry. So I claim there are 6 ways of taking the convex hull of 2 points in the plane. So these are these creatures that we've already seen, and these are the 6 combinatorial types of, well, taking the convex hull of 2 points in the plane, right? So there are these 3 possible shapes, but then I'm going to keep it labeled, so I'm going to distinguish this 1, 2 from this 2, 1. So there are 6 types like this.
But what if there's no band?
Yeah, these are the generic ones, okay? So I'm talking about the generic types correspond. Yeah, they could coincide, right? I mean, for instance, the point is a possibility, right? I could have 2. So these are the generic types. So they're supposed to correspond to the triangulations of the Toblerone.
Why do we have to keep track of this?
We don't have to. And in fact, we will not on the next transparency, just to kind of, fix our mind. If we have, so the other one, if we take, now let's try to get this right. So if we take, so that's actually n equals 3 and r equals 2. Then if we take r equals 3, n equals 2, then what we're doing is we're taking 3 points on the line. And let me assure you, the tropical projective line is really just the ordinary line. So there are 6 ways of taking the convex hull of 3 points on the line. And in this theorem, I like to distinguish these 3 types. And then, of course, the triangular prism, which is delta 1 times delta 2, has 6 triangulations, all of which are regular. And so these 3 sets with 6 elements, they're all the same. Now, to answer Serkan's question, of course, they're all up to symmetry. I mean, in each of these 3 sets, there's an obvious symmetry, and I mean, these 6 things are all in the same orbit with respect to the symmetry. So to make it a little bit more interesting, how many triangulations does, well, maybe the second to next case, if you take a triangle times a tetrahedron, then that's a 5-dimensional polytope. How many triangulations does it have? Actually, this is sort of kind of the last case where the triangulations are all regular. And the answer after modding out by symmetry is 35. So thanks to Jörg Rambau for calculating large numbers like this using TOPCOM. So there are 35 after modding out all the symmetries. There are 35 truly distinct tropical quadrangles in the plane or tropical triangles in 3 space. Okay? So this seems to indicate that triangles in 3 space are the same thing as quadrangles in the plane. Okay. So here's how we compute small examples, and I think we'd be very, very happy if somebody from computational geometry could get interested and look at this sort of both from a practical and from the complexity point of view. So I think many of the techniques that people know, such as reverse search and so on, can be used to design very efficient algorithms for doing this. And we'll see at the end that this has some very practical applications. So here's how we do it. Let F be, I call that the hyperplane fan. Well, it's actually the red thing is a hyperplane in the plane. So in general, this is the codimension 1 faces of the outer normal fan of the simplex, or the fan for projective space. So I call this red thing down here, I call that the hyperplane fan, and then we draw minus F. So there's F. F is the hyperplane together with its fan, and then there's minus F, which is the same thing, just rotated by 180 degrees. That's step 1. Let's start with that. Step 2, let's tag on a copy of the fan minus F at each of the points in consideration. So we have these points V1, V2, up to VR, and we place a copy of the fan minus F by placing the origin on top of the points Vi. Then the next step, we take the common refinement of these fans, right? So if you have R fans, they all have undergone parallel translation with respect to each other. We intersect them. We take their common refinement. That's a polyhedral decomposition. That's a subdivision of n-1 space into pieces that are convex polyhedra, ordinary convex polyhedra, actually both ordinary and tropical convex polyhedra. But in any case, they're ordinary polyhedra, some bounded, some unbounded. And then step 4 is to take the union of all the bounded faces of this cell complex, and that is the tropical convex hull. So here's an example of a tropical triangle. So we want to compute the convex hull of this point, and that point. Then we place a copy of this fan minus F at each of these 3 points. We look at the subdivision of the plane that's induced by that. And then there are a bunch of cells of dimensions 0, 1, and 2. And we color in green all those cells that are bounded. And we can see there's one bounded sort of pentagon, and there's 6 bounded edges, and there are also 6 zero cells which are necessarily bounded. So this is a polyhedral complex of F vector 6, 6, 1, and experts will see immediately that's contractible by construction. Okay? So that's a way to visualize one way of calculating the convex hull of R points in n-1 space. Okay, here's an alternative way of describing it that makes it more transparent, makes the connection to the product of 2 simplices more transparent. So here is a high-dimensional version of the same thing. So I'm going to describe a different algorithm which actually turns out to be the same. Okay? So again, we like to calculate the tropical polytope, the convex hull of V1 up to VR, together with its natural cell decomposition. So here's now my notion of combinatorial type. This construction here gives me the convex hull, but it gives me the tropical convex polytope together with the cell decomposition as a union into ordinary polytopes, well, which happen to be tropical polytopes as well. So here's how we do it. Step 1. Let's look at the n plus r minus 1-dimensional space. So this is a space that has the symmetry between n and r. So I take the space r to the n plus r, but I mod out by the 1-dimensional space spanned by the vector, 1, 1, 1, 1, 1, n copies, and then minus 1, minus 1, minus 1, r copies. So this is Euclidean space, vector space of dimension n plus r minus 1. Let's look at the following unbounded ordinary convex polyhedron. I take the set of all points x, comma y in this space such that xi plus yj is less or equal to vji for all I and j. I hope I got the order of j and I right. Mike nods. That's okay. So vji is the ith coordinate of the jth vector that I'm interested in taking the convex hull of. So let's look at this unbounded polyhedron. And then step 2, there's a piecewise linear isomorphism between the desired tropical convex hull and the complex of bounded faces of this polyhedron. So you just take this polyhedron. This is some unbounded polyhedron of dimension n plus r minus 1. Its bounded complex, so the subcomplex in the boundary of this unbounded polyhedron that consists of bounded faces, is much lower dimensional. Its dimension is less than the minimum of n and r. And then turns out that this bounded complex is contractible. All bounded complexes are. And that's actually the same as the tropical convex hull. Okay, so I indicated now this is really this high-dimensional construction. This construction is polar to taking regular subdivisions of a product of two simplices. The left version can be reinterpreted as the Cayley trick that some people have looked at. But in any case, we get the corollary that tropical polytopes with R vertices in n-1 space really the same as tropical polytopes with n vertices in R-1 space. Let me state this in even more succinct form. So let's take one of the creatures from this beautiful picture. So here's one of them. So actually, if you have any matrix whatsoever, then the convex hull of its rows equals the convex hull of its columns. Okay? This is sort of amazing, but it's true in tropical geometry. So if you have any tropical matrix and you take the convex hull of its rows, then there's a canonical identification of the convex hull of the rows with the convex hull of the columns. Now we know, because in ordinary geometry, that's not true. We know that that's true for the linear span. If you have a 4x6 matrix of rank 2, then of course, the row space and the column space have the same dimension. And with a little bit of effort, you can produce an isomorphism between the two. And that's true too here, but it's true for the convex hull. So here's a small example. So let's start with a 3x4 matrix. So if I look at a 3x4 matrix from the point of view of the columns, then what I get is I take a quadrangle in the plane, and it looks like this. And I hope now I got the points right, because that's essential. So these are the extreme points. The convex hull of these is this picture. But if I look at the rows, then I get a triangle in 3 space. I have 3 green points in 3 space. Now I take their tropical convex hull, then I get some bent, creature in 3-dimensional space. So there's a little pentagonal cell and another pentagonal cell, and they sort of lie in 3 space, not in the same plane. And this small triangle folds up, and then this tiny little stick sticks out. Okay? And they are actually the same polyhedral complex. And again, one way to see that is that this description on the middle transparency, or its polar version in terms of triangulations, is simply symmetric in R and N. So this tells us that there's actually an involution on the set of all tropical polytopes. Okay. Any questions at this point? So these are 2 ways of constructing the tropical convex hull. And as I said, I think it would be very interesting to look at this from the point of view of computational geometry, both maybe a complexity analysis and, fast implementations. Okay, so I'm not going to... let me state 2... Before I shift gears, let me state 2 more results about tropical polytopes. They're kind of interesting. Slightly less easy to prove, but not so bad, is that the intersection of 2 polytopes is a polytope. So in ordinary geometry, you sort of first prove duality. You have sort of the H presentation and the V presentation of a polytope. That's not quite true. We have a separation theorem, but it's quite a bit more delicate. But it's still true that the intersection of 2 tropical polytopes is a tropical polytope. And then here's sort of a nice formula for the F vector. So let's look at a generic polytope. So I'm going to say that a convex set V is in general position if every square submatrix of the matrix of coordinates is tropically non-singular. Well, I'll talk more about this tomorrow. So there's a tropical notion of determinant. And then for a matrix to be tropically singular means to be, on the variety of this determinant, and to be non-singular means to be outside. So if you have, I'm going to say a matrix is generic if every square submatrix is tropically non-singular, and that's a sort of a general position condition. If that is so, then the F vector, the face vector, of the polyhedral complex, so I told you a tropical polytope comes together with the cell decomposition, depends only on R and N, and in fact in a symmetric way, as it should. So the number of I-dimensional cells in the decomposition of a tropical polytope P is given by this nice trinomial coefficient, R plus N minus 2 minus I factorial, divided by R minus 1 minus I factorial times N minus 1 minus I factorial. So here's a little example. So again, if we take our 35 types of quadrangles in the plane, they were all generic. Actually, these were all the generic types I printed. And they all have 3 two-dimensional cells, 12 edges, and 10 zero-dimensional cells. Okay. So in the remaining 9 minutes, I'd like to talk about an application. Turns out that, like every good concept, this has been discovered a long time ago in many different forms. And in one guise in which tropical convexity appeared is the work of Andreas Dress. Andreas Dress has been working with collaborators on problems in bioinformatics, and his papers are, to some of us anyways, not so easy to read, but we found out that, in fact, it's there. So here's the problem. So it's the problem of constructing phylogenetic trees from genomic data. So let's say we have 5 taxa, 5 species, the rat, the mouse, you and me, and maybe another one. And each of these is given by, encoded by a long string of letters over some finite alphabet, for instance, the 4-element alphabet with letters T, A, G, and C. So we have some big data set like this. Okay, this is a small cartoon example. Now, you can think about these data as giving you a metric space, right? So you look at the Hamming distance between any 2 strings, and it gives you information about how far they are apart. So, for instance, the first and the second string differ in exactly 2 places. Maybe the first place and the fifth to last place. So I say that the distance D12 between the first 2 strings is 2. And so on. So for instance, the last pair, so 4 and 5, they differ in 3 places. So this is a finite metric space on 5 elements, clearly satisfies the triangle inequality. And here we just take the Hamming distance. So there are many other variants of this problem, and Lior Pachter, who's here, is an expert on these things. So this is the Hamming distance giving from some sequence data. It's a bunch of words, finite set of words, and the same length, say, in finitely many letters. So what we'd like to do, the ideal scenario in phylogenetic analysis, is to reconstruct the unique tree that is that metric space. Okay? So in this case, actually, I can draw a tree. And so here's a tree, but I should think of this as a metric tree. So each of these green tiny segments have unit length. So they're supposed to have unit length. And then there's a unique path between any 2 leaves. And there's unique distance. So for instance, the distance from node 4, leaf 4 to leaf 5 is 1, 2, 3. Okay? So the distance, between 1 and 2 is 2, and that's exactly these blue distance data. So this green tree realizes this metric space. So this is actually this is a metric tree, and this is a tree metric, right? So, and then this tree gives us a lot of information. So maybe under some extra hypotheses, we can find out that Adam and Eve are here, and then it gives us information about the rat and the mouse and you and me. Okay, so that's the ideal scenario, is given a finite metric space to determine whether or not it's a tree metric, and if so, construct the tree. So it turns out there are standard algorithms, there are theorems from the late 60s and early 70s that characterize tree metrics among all metrics. And there's something called Buneman's 4-point condition. So think about this for a second. Let's concentrate on a subtree of 4 leaves. So let's concentrate on 1, 2, 4, and 5. Well, it turns out that the distance from, if you look at the distance from 1, 5 plus 2, 4, that's the same as 2, 5 and plus 1, 4, right? And it's bigger than 1, 2 plus 4, 5. Yeah, so you take 4 of these guys. There are 3 sums of pairs of distances. And in a tree, the maximum has to be attained twice. And that's actually necessary and sufficient. That's called the 4-point condition, and that characterizes tree metrics. And let's reinterpret both this condition and the resulting algorithm in terms of tropical convexity. This slide is called the injective hull of a metric space. This term goes back to a 1964 paper by Isbell, which I learned about in the work of Dress and his collaborators. So Dress has been working in tree theory, for about 15 years. Okay, so let's do the following. Let's look at a finite metric space D. So I encode that as a symmetric matrix with zeros along the main diagonal, and let's say positive entries off the main diagonal. So I look at the matrix whose entries are D, I, J. So a finite metric space gives me a symmetric n by n matrix with zeros along the main diagonal, and then positive entries off the main diagonal. Now, saying that all triangle inequalities hold just says that D squared is equal D, tropically.
You want minus D times D?
The equivalent, actually. Okay, if you think about Dijkstra's algorithm, so saying that D squared is already D says you make no more progress in Dijkstra's algorithm. You can't short circuit in Dijkstra's algorithm, and that's actually also equivalent to the simultaneously holding of all the triangle inequalities. So you can say, something is a metric space if it's a symmetric matrix, 0 on the diagonal, positive outside, which is idempotent. D squared is equal D. So let me write PD for the tropical convex hulls of either the rows or the columns of the negative of this symmetric matrix. So here we have to, this sort of min-max thing. So we have to take the convex hull. So that's the convex hull of n points in n minus 1 space, and we have to take the rows of a negative D. So then we have the following theorem, which is really sort of a reinterpretation of what's known in the phylogenetics community. The following 3 conditions are equivalent for a metric space. 1, D is a tree metric, so D can be realized by a tree. 2, this tropical polytope, PD, has dimension 1. Okay, so it has dimension at least 1, but it has the minimum possible dimension, which is 1, if and only if it's a tree metric. Buneman's 4-point condition, the one I talked about on the other slide, we will see tomorrow, can be interpreted as saying that negative D is a point on the tropical Grassmannian of lines. So that's the classical Buneman condition. And those 3 things are equivalent. If that is so, then the tree is the polytope. Okay, so if any and hence all of these conditions are satisfied, then the tropical polytope PD is the desired metric tree with the induced, the metric I mentioned earlier. There's a standard L infinity metric on projective n-1 space. And then you can simply embed the finite metric space into PD by just taking the rows of the matrix, right? So you take the convex hull of the rows. So certainly the convex hull contains the rows. So PD is another metric space that contains the ones, and it's this one, right? So we take this, this, this. So the classical additive tree reconstruction algorithm of phylogenetic analysis amounts to taking the tropical convex hull. So in the work of Dress, this was generalized, or he looked at the situation when the polytope is not necessarily one-dimensional, but could have higher dimensions. And it turns out that his object, or rather Isbell's object, is equivalent to ours. So theorem, the tropical polytope PD equals the injective hull of the metric space D in the sense of Isbell and Dress. And that's potentially of interest in biological applications.
So is this retraction you're talking about there, is that the nearest point condition?
I will be happy to discuss this paper with you over coffee. Yes, okay. So highly original, but yet not sufficiently appreciated contribution, indeed. So this is the last transparency. So there's the group of Dress. There was actually an implementation by Daniel Huson. There's a code called splits tree where people, I mean, in real life, the distance data are approximate. So you never get a tree, right? You never, ever. You don't know the DIJs exactly. You know them approximately up to so many digits. So you never get a tree exactly. So all the algorithms that exist produce some nearby tree that's supposed to be close to the data. The idea is that here is that this polytope PD is sort of the universal complex, the universal object that parametrizes or contains all the trees that will be produced by all the various phylogenetic programs. There's a software by splits tree where this is actually done and higher dimensional cells occur. So this is an example from this paper of Dress and collaborators. So here's a tropical polytope, maybe a high dimensional phylogenetic tree where you have some taxa and then you have some parallelograms. So these are some two-dimensional cells. To hear more and join us, Leo and I are going to have a seminar this fall down the hill, and you're welcome to talk to us about that. Thank you for your attention.
Questions, remarks, comments, protests, additions, priorities? And I have a few questions, and one would be just on this question and on this example. I mean, it seems surprising that the answer should be two-dimensional here, right?
Yeah, it is surprising. Okay, so the splits tree isn't actually the injective hull. It's sort of a certain projection, sort of a simplification. Yeah. So they did not have. So we have a big advantage, right? We have all the computational geometers here who can help us to design really good algorithms for computing the polytope PD, and so they only got sort of a two-dimensional view of the object that you really want. Let's talk about it over coffee. So the work is very categorical. So there's a notion of injective object and injective hull in category theory. And so you can think about the category of metric spaces. And then there's a notion of an injective object in this category. And these are exactly the injective hulls of the finite metric spaces. But that's explained in this paper, not yet sufficiently appreciated paper.
Yeah, so I think there's already been a lot of advertisement now for the coffee break. So let me also advertise that in 25 minutes we'll hear the second talk by Joel Haas. So we'll come back for that. Also, let me remind you that